So the project name is VADER. I would like to, we're a little geeky on that side. I think that's why we actually got the project funded by DOE. It stands for Visualization Analytics with High Penetration of Renewables, Distributed Energy Resources, really. And we just selected just the ones that we think could make VADER. So anyway, so the project's funded by the Department of Energy's Solar Energy Technologies Office. We have Southern California Edison and Opal RT, a hardware-in-the-loop company, SunPower and ChargePoint and Arizona State University, as well as Stanford University as our partners. I'm just going to sort of talk about what we're going to do, what we're doing, why we're doing it, what we're doing, and how it's going to, we think, is going to impact how we're running the power system. I didn't have this slide, but I thought it would be nice to sort of talk a little bit about the changing grid. You're probably aware that our grid is changing, and part of it is because the grid as a whole was designed so that the generators generate and consumers consume. But now we're seeing that but now we're seeing that there are actually, so we're changing from being a consumer-only producing at the same time with our solar rooftops, and so we're becoming more and more producers as well as consumers, so we're calling us now prosumers. We have, of course, electric vehicles. Some facilities have combined heat and power systems. We've been adding wind and solar at the prosumer side as well as storage. Same thing, large-scale distribution system size, wind, solar, and storage, and as well as on the transmission system. So we're adding a lot to our existing system that was designed to be one-way operation only, with protection devices that eliminate the backflow of power. So that's completely changing, and we have the same system. And this is mostly driven by all of these mandates that are national, and sometimes in California, it's very California-centric mandates and goals that are put together by the governor's office or the commissions, the Energy Commission, or the Public Utilities Commission. So there are a lot of changes that are happening. And over the last, I would say about 5 to 10 years, we've been putting a lot of sensors on our system too. Not that we're doing anything with those sensors, and I'll talk a little bit about that, but we've invested, as California, we invested $4 billion in smart meters. We are putting phasor measurement units on the transmission system that capture really high rate data. And we have about 75 of those. 300 of those were put in the entire Western Interconnect. 75 of those are in California only. We have micro PMUs, again, phasor measurement units on the distribution network, again, producing a lot of data. High fidelity data. We have PV generators that capture data every second, maybe reported every minute or every 10 minutes or 15 minutes. We have EV charging stations. I'm sure you've seen those on campus. They collect data about 15-minute granularity. We have smart meters that capture data anywhere from a second to hourly data. And then, of course, interval meters, which we've had for a very, very long time for large commercial and industrial facilities. So lots of data, but all of this data isn't being used. So the point of our project was that if we could use the data, wouldn't it be nice? And what would we find out about the power system as a whole? And there are other issues that we're facing as well. There are a lot of more active devices on the system that are on the distribution system that monitor the system and do control on top of it without any intervention. Utilities are unaware of existing deployments, small deployments, and for them to install sensors everywhere is not reasonable. They don't keep track of these, especially if they're residential scale. You get an interconnection agreement, they file it somewhere in the cabinet, no one knows who has how much. And then the bidirectional power flows and overvoltages are major issues as we go to a bidirectional system. So there is a need to really understand and gain more visibility into the distribution network and see what's happening, basically. And of course, data-driven models have been really successful. We typically run the power system using physics-based models. Kirchhoff laws is something that we continually used for state estimation, power flow calculations. But going forward, we know that these devices that are at the grid edge, the behavior, the way that the folks are using their systems that are producing and consuming sometimes, we have no sort of visibility or even sort of physics-based models for these kind of interactions. So we thought about a couple of years ago when we proposed VADER that it's time to really think about how the data-driven models can be used in the power systems world. And of course, if you look at power systems, it's a very hardware-driven, hardware-focused, hardcore, power systems engineers that are not software engineers, that don't understand about data, that haven't used anything but maybe Excel spreadsheets to date. So very different culture, very different group of people. And of course, you know that data-driven approaches have been extremely useful. There have been a lot of algorithms that are developed, and we haven't even really looked at some of those algorithms and their applications in the power systems. So our starting point is there's already so much out there. Let's sort of figure out what can be applicable in this world of power systems. Please stop and ask any questions you may have. I am just sort of going. So the project is about how can we monitor and plan for the grid using much more data than we did before. Typically, we have models, physics-based models that are either open source, tools that are open source, or very expensive modeling tools that folks buy and run their simulations on. And the idea is that let's try to move away from them and let's try to figure out what the data-driven modeling can help do for the power system. Let's just scratch the surface. We know that it's not going to solve all the problems or all the issues, but let's see how far they can go. So so we said, let's collect as much data as we can from the power system. The smart AMI stands for Advanced Metering Infrastructure, the smart meter data, micro PMU line data, SCADA data, solar generation data, electric vehicle charging data, and weather data. Let's sort of collect these, dump them into a database, clean them a little bit, organize them, and then start looking at what to understand what is happening on the power system right now, and what if analytics, sort of scenario analysis on what can we, if things change, how would they impact the power system. And we went to the utilities and said, what are the use cases? What are some of the applications that you'd be very interested in? And they said, well, we want to understand where we should put storage, where we should put storage, where we should put solar. We want to understand what kind of voltage issues that we're seeing in the system and how to predict those voltage issues. How can we plan for flexibility now that the resources are more manageable, deferrable in their consumption? And how can we continually evaluate the performance of the electricity grid? So a little bit about what we've done. We actually have developed about 7 or 8 different analytics for the power systems operators and planners. We demonstrated some of these with historical data, all of these with historical data, but validated some of them with real data as well. We held workshops and laboratories because it's not enough that we create these wonderful analytics tools. If no one's using it, we're not very successful in what we're doing. So we bring utility engineers, planners, and operators into our lab and teach them how to use these tools. And I'll talk a little bit about the platform we created so that they can actually use these tools fairly easily. Some of these analytic tools are being adopted by Southern California Edison in their own facilities and being used. And then we sort of started growing. We started very small with small models and small analytics and have been growing at those capabilities and testing them throughout the development of the project. I have about 2 slides that talk about like what are the analytics that we've developed, what are the data streams that we use, what is the training data that we use. So I have them. I'm not going to go over them. You will have them in your slide set. This is a question that I get quite often, and different analytics, we use different kind of data sets, and I'll just leave it for you to take a look at later on. But what I want to talk a little bit about this is the platform that we created. Initially, we started with, and I should probably go to the next slide, Initially, we started with this homemade platform where we had Spark database, we had some models that are running in the background, some Django D3 libraries for visualization, and we soon realized that it's not very scalable. We couldn't communicate these pieces and how to put them together for a utility. The folks there were clueless about how to put it together. They knew about AWS, they knew about Google Cloud, but they didn't really necessarily know about all of these parts and pieces together and how to put them together.
You're using scalable there in the sense of the reproducibility of the process and getting it into the hands of the users rather than scale on the technology.
Both. Both. I want this, I want to be able to handle a lot more data and being able to handle the entire utility data, but also in terms of probably growth and scalability of use. I want to create users at the same time because we want people to use these tools. So we moved to an AWS platform. We use a lot of the Lambda functions, and the data comes in, we store it, we create data descriptors, and then the biggest problem here is people spend a lot of time creating schemas for power systems data. There are no standard schemas. Everyone's been developing their own stuff, more or less. Companies like C3 IoT have a great library of schemas, but they wouldn't share it because it's their proprietary development. They spent millions of dollars on that. So our goal is to start building these schemas ourselves too, but some of it we've been experimenting with trying to get away from schemas and try to figure out how we can use graph databases and try to create relationships among the data sets and things like that. So there's a batch analytics capability and stream analytics capability on the platform, and also we have integrated Jupyter Hub so that any data scientists at a utility can pull their data in and create their analytics or even use our analytics to begin with. So I'm saying any data scientist, just to give you a sense. Southern California Edison only has one data scientist. PG&E has 3 data scientists. These are large companies, they're running the grid, and it is sometimes really disappointing to see that they're not doing much more with their data. They really want to, but they don't have the capabilities. And when they try to hire, they're really competing with the Facebooks and Googles of the world, so it's very difficult for them to hire even the right people. At least that's what we're hearing from them. So first year, we just developed something to show DOE. We realized it's not really scalable, so we moved to the AWS with the Grafana interface. The map on the right is all the data sources that we have. It shows 2 substations in Santa Ana. This is the area where the San Onofre nuclear generation station was shut down, and there's a congestion issue through the transmission lines. So they're trying to figure out how to have local resources that can meet the needs of the city. Yellow shows the location of the SunPower data, SunPower generators, and then the green shows the green pings show the location of the charge point stations. Okay, so really quickly, I'll go through 3 analytics. I'll actually start. I know I don't have much time. So one of the things that the utilities said, we really want to know how to, what's behind the meter solar looks like. We don't keep track of the small solar deployments, less than 10 kW. So can you tell us which customers have how much solar, so that when we aggregate them, and if there's a cloud or solar eclipse, we'll know exactly how to manage that location of the grid. So we're using SCADA measurements, which are 4 seconds in sampling, and AMI data, that is AMI, the smart meter data, that's downloaded every night, and it's 1 minute granularity. So we have validated our algorithms using a public data set from Pecan Street in Texas, and we showed that we are pretty good at disaggregating solar given the net load. So we have one sensor line sensor at the substation level. We have AMI data that gives us net load in each of the homes, and we have a solar proxy. Just using those data sets, we're able to pretty accurately show the solar consumption or solar generation behind each home. So each of these is a home. This one is day ahead. Dark lines are actual data. Lighter lines are predicted. And you can see that there are some issues sometimes, but overall, we're seeing a lot of, we're calculating a lot of the data. And there's some room for improvement always, but I think as we extend it to other data sets, we'll get a chance to improve as well. This algorithm actually won an R&D 100 award. The folks who developed it at Berkeley Lab came to SLAC and started working with us and expanded significantly beyond their initial use. Someone said switch, so thank you for that. That sort of builds into this slide. We looked at, so utilities don't know the switch configuration of all of their network because they don't have sensors on all of the switches because it's expensive to put sensors on the switches. So one of the algorithms that we've been developing is, can you actually strategically locate the sensors and only install a subset of sensors and reconfigure the entire switch configuration, detect the entire switch configuration of a network. So we applied that algorithm in this Camden substation at SCE, and there are about 112 aggregated loads, different phases. There are 123 switches to monitor. With our algorithm, we were able to put sensors on only 12 of those switches and recreate detect the switch configuration of the entire network, even though the switches could change and even though there are delays in the data. So this has been a very promising, computationally expensive, but promising algorithm as well. So the last thing I want to talk about is this machine learning-based power flow. Power flow is the key to power system calculation. And again, as I said, it's based on Kirchhoff's law, and you need to know the line connectivity options and parameters to be able to accurately calculate that. With our method, you don't need line information. We build correlations. We use support vector regression, so it builds correlations among the different data errors. So we don't need the system to be observable. We can handle missing data really well. And then instead of calculating any steady state, we can predict the voltages and calculate power flows over time, which is a huge improvement given what we're doing. Just to give you a quick idea about how it works, we're very good at taking a load or demand and projecting it. Forecasting load, we're pretty good at it, especially if it's aggregated, the noise goes away. What we can't do, because it depends on a lot of different factors, is voltage prediction. It's impossible almost to predict voltages at different places in the system. So what we do is create a mapping between the power and the voltage. We predict voltage and then reverse map to extract the voltage information. And then we say, okay, if it's going above a certain NC requirement, we're saying that there's a voltage violation tomorrow at that time so that operators can manage it based on that. We've tested our method against the traditional methods very thoroughly, and the performance has been a huge improvement. Again, I don't want to oversell it because we've done only on IEEE 123 bus system, and we're now transitioning into the real data systems, and we'll have a better sense of how it performs with actual data. All right, so I talk a little bit about sort of the workshops and the learning labs. We try to, whoever we can grab, we put them in the lab and we try to teach them these methods because we think that this should be the future of power systems planning and operation. We always think about, if it works, does it matter, right? We can do these very cool projects, and we can come up with great ideas, great algorithms, but does it really matter? Who will use this? And if they use, is it going to lead to some impact? We think that there is a huge opportunity with utilities and state agencies to use these tools today. Unfortunately, they don't have the right people who can set this up or understand or use it. So we're building the airplane and also training our people at the same time, which is a lot of work. We think that there's a lot of opportunity for small utilities that don't have large IT groups to do this and provide them as a service. So it could be a platform as a service or a software as a service for these small utilities or community choice aggregation companies. We know that the utilities can use these analytics directly, some big ones that are more equipped to do that. We think that these platforms and the data analytics could be easily integrated to advanced distribution system management tools and also distributed energy resource management systems. And we've been in communications with Siemens and Schneider and ABB to see how we can actually incorporate more data into the system. And then, of course, platform as a service and a software as a service are options. Lots of publications and all of the analytics I talked about. 2 pages, 2 slides of publications. I'll leave these as well so that you can take a look at them. And I just want to thank you to this large team made up of data scientists, software engineers, platform developers. A big addition to our team is there's this Carnegie Mellon Silicon Valley campus, and they have a practicum that they do every year. We steal 5 to 10 students every year who are expert software engineers who are interested in managing platform development and software management. And they come in and stay with us at SLAC for over pizza and beer. Not at SLAC, at Stanford, the beer, I mean. And they work with us, and they work really hard. And this was the platform development was with their support. The analytics development is with SLAC scientists and Stanford faculty and students. So exciting times for power systems, and we're really excited to be at the leading edge of that discussion with power. Yeah.
Does Stanford have a degree program in power systems engineering? Because
No.
Berkeley abandoned theirs.
No, yeah, so Stanford and many other universities at that level don't have power systems. The good power system schools are University of Washington, Wisconsin, Georgia Tech, ASU. Yeah, we don't have a big power systems group here at Stanford.
So it seems like power generation and distribution is a pretty global, international phenomena.
Mm-hmm.
How would you compare where you are with what's happening internationally on this? Is there a European version, a Southeast Asian version, Australian version, and so forth?
Yeah, so I run a initiative at Stanford called Bits and Watts. And as you can tell, we're trying to combine bits with watts. And we have a lot of international utilities that participate as members, and this is new to them too. I think part of it is data security and privacy is a big issue. In Europe, they just announced GDPR, which is a big data privacy law. That's a big barrier for a lot of the utilities as well.
So one of the things we heard yesterday from ER doctor, I guess, or ICU doctor, was that it's necessary to get deployment of any of these technology tools, you need to make sure the incentives are aligned. The common knowledge is that utilities are highly regulated, very stable businesses. Is that one of the reasons why it's difficult, because they don't have any incentives to improve? If they save money, it doesn't go back to them, it goes to somebody else?
I think regulators are starting to push them to improve. The smart meter data not only captures demand data, power data, but it also captures voltage data. And utilities are not looking at the voltage data because they don't want to know what the voltages are at the grid edge. They can be really high, they can be really low. And if their utility commissioners know about that too, then they'll have to do something about it. And they don't want to, right? But the commissioners understand that that's a data set that they need to look more and more into. And now there are some new rules and proceedings that are coming out to just look at that data that's being captured with smart meter data, especially on the regulated utility realm.
You mentioned the voltage up and down or voltage instability is one of the use cases. Are there any other use cases that you're trying to solve with the analytics?
Yeah, so there's a lot of reliability metrics that are typically captured, but again, snapshot, so we can keep track of reliability metrics, such as downtime of the system and typical time. So that's not something that's typically kept up. As we incorporate more distributed energy resources, we can capture their impact more and more. The flexibility of the system, being able to predict it so that you can manage the variability of renewable generation, that's something that's not being done necessarily well. So there are lots of other use cases. There's security use cases, resilience use cases that we're looking at. Imagine we can combine this with satellite data and other image processing capabilities, which we plan to do, then it becomes a different thing. Maybe we could have predicted the fires in Santa Rosa or in Southern California.
Any other questions? Cool, thank you. Thanks a lot, Sila.